In this tutorial we will take a closer look at a divergence test. The purpose of this test is to check whether a given series satisfies a particular property which is necessary for the series to converge. Hence, if that property is not satisfied, we conclude that the series does not converge. We start by stating the test. Let us suppose we have given a series taken over the sequence an. Now if the series converges, then the limit of an as n tends to infinity has to equal 0. Consequently, if we turn this around, we can say that if the limit of the sequence an as n tends to infinity is not equal to 0, then the series does not converge. That means the series either diverges to plus or minus infinity, or its limit doesn't exist at all. In short, this test allows us to learn something about the series by studying the limit of the underlying sequence. Let us consider some examples to see how the divergence test works and what its limitations are. Consider the series taken over n divided by n plus 1 for n running from 0 to infinity. This series is not a p-series or a geometric series or alternating series, so we can't apply any of the theory we have for those types of series. Hence, in order to gather more information about this series, we might consider taking the divergence test. The divergence test asks us to study the limit of the underlying sequence of our series. Here the underlying sequence is given by an equal to n over n plus 1 for n greater or equal to 0. Now if we calculate its limit, we see that the limit equals 1, which of course is not 0. Now according to the divergence test, we must conclude that our series does not converge. Furthermore, since we are only adding positive elements, we can say that the series diverges to plus infinity. This example shows that the fact that the underlying sequence does not converge to 0 is enough to conclude that the corresponding series does not converge. Further arguments allow us to give a more precise answer in this case. It is very important to understand that the divergence test only works in one way. Only if the limit of the underlying sequence of a given series is not 0 are we able to draw a conclusion. If the limit of the underlying sequence turns out to be 0, then the test fails to tell us anything about the series itself. That is the common mistake, to assume that because the limit of the underlying sequence is 0, the corresponding series has to converge. This is a false conclusion, as we can see in the following example. Consider the harmonic series. That means we sum over the sequence 1 over n for n running from 1 to infinity. Then the underlying sequence is 1 over n, and for the limit of the sequence we get 0. In this situation the divergence test is inconclusive. However, knowing that the harmonic series is a p-series, we can apply our knowledge for this type of series. Recall that in this case p equals 1, and therefore the series diverges to plus infinity. This shows that despite the underlying sequence converging to 0, the series itself does not converge. In fact, it diverges to plus infinity.